So hopefully you did the assigned reading so that you will have read it once, and then once we go through it here, and then once we finish the activities in lab this week, it will start to click and make sense to you. So So inverse square law is based upon what happens to the intensity of the beam when we make changes to the SID. So when we change the source to image distance, it changes the intensity of the beam. And we know that the source to image distance is the one of the primary exposure factors, and it is the one that is set in the room, not at the control panel. So how does it affect the intensity or the quantity of the beam? So in radiology world, referring to quantity, how much, the amount. Okay, so when we're talking about the amount of photons. Hello. So don't think of it in terms of quality of the beam or penetrating ability of the beam. That's not what we're referring to when we talk about intensity in radiology terms. So we're talking about quantity, how much. So how does changing the SID affect the intensity of the beam? Well, we can talk about that in the inverse square law. And so the actual definition of inverse square law is the intensity of radiation is inversely proportional to the square of the distance from the source of radiation. So that's a lot of words in there. But if you break it down, you could figure out exactly what this is talking about just from what we already know about some different things that we've talked about relationally. Okay, so the intensity, meaning the quantity of radiation, is inversely. So that means what? If opposite. Yes, it means opposite. So if SID goes up, that means intensity is going to go down. So inverse. Proportional, meaning changes in the same amount. But this is to the square of the distance from the source of radiation. So this little picture here is just a good illustration. And one thing that you're going to see with from here on out with some of the concepts that I teach is using a flashlight is a great way to help you understand what is happening to intensity, to when we get to spatial resolution, to distortion. So you can actually take a flashlight and see a lot of these concepts. And so in the top picture there, you can see that they're shining the flashlight and they're pretty close to this tree in the front. You can see that that light is very bright, but it's not covering a very big area, right? But in the second illustration on the bottom, you can see that now they're shining the light out further away so they can see the entire tree, right? But what about the brightness of it? What has happened to the brightness? It decreases, right? So think about when you take a flashlight and you hold it super close to the wall. What do you notice about the brightness of the light, first of all, compared to if you hold it back here? Higher. Yes, so it's brighter when you're close to it, right? Is it covering as much of the wall when you're as close? No. So this is one example that you can think of in your head to help you remember, okay, what is happening to the intensity of the beam when the distance increases or decreases? This also is an illustration that shows you So also I wanted to go back because I realized I had taken that picture out of the PowerPoint for last week, and I don't know why. I didn't mean to. But so related to intensity and the shade of gray in this picture. So where is the being the most intense? 1, 2, or 3? 1. It's the most intense at distance 1 because that is closer to the source, right? So as you increase your distance, that intensity is going to go down by the square of the distance. So if you look at this picture, it's another way to just visualize what is happening. So at distance 1 in this picture, you have 4, and this is totally hypothetical, right? Just to give you a mental vision of what's happening. So in 1 square, you have 4 light blue, and then you have what looks like 4 orange, 4 purple, and 4 light green dots. Let's pretend like those are photons, okay? So what happens to the number of dots or photons in each square of that as the distance doubled?
Still the same.
No,
They
there's
spread
one quarter
As
of dots.
There's a right. So the intensity decreased by a factor of 4, right? Because it's to the square of the distance. So if we double the distance, that's by a factor of 2, right? 2 squared is what? 4. So as we doubled our distance, now the number of dots has now spread out over a larger area, right? So now instead of there being 4 dots in 1 square, there's how many? 1. So there's a fourth of the intensity that there was at distance 1. Making sense?
Yeah.
Okay. There's also on Blackboard, I don't know if anybody looked, but there's a video. Did anybody by chance peek at that video related to inverse square law? It's not specifically talking about radiology, but we can talk about inverse square law with a lot of different things. We can talk about it with light. And so there's a video that uses the example of a spray paint can. So think about that. Anybody ever spray painted anything? Okay, so what happens to the quantity of paint when you're closer to the thing you're painting? When you're spraying, yeah, it's a lot more paint, right? As you move back, the area is getting bigger that you're painting, right? But it's thinning out. So just another example of something that you can think back to if you get confused. Now, writing this, so we're going to see from here on out in my class, we have a lot of formulas. And so that video says, well, it's not really a formula or an equation, it's a ratio, but we just call it a formula in the world of radiology. So the inverse square law is a formula that you have to memorize. And when I say memorize, it's not really memorizing if you understand what is happening, okay, in what inverse square law is. But you can write it this way. The I, what do you think the I stands for? Intensity. That's what we're talking about here. How does the intensity of the being change with changes in distance? So I1 is intensity 1. I2 is intensity 2. You can also think of those as old and new. I like to think of them that way. I think that is an easy way to, when you're setting formulas up. So the first intensity over the second intensity is going to equal the second distance over the first distance squared. So why do we have it in this kind of relationship? It is a cross multiply, but
Because of the inverse.
Because they're inverse to one another, right? if distance goes up, intensity goes down. Yes. So that's why they're written that way. So what I'm saying here is it wouldn't be wrong if you just mirrored that, flipped it. Okay. So what I'm saying is you could also write it as intensity 2 over intensity 1, but then what would have to go on top over here for distance? Distance 1 over distance 2 squared. You're going to get the same answer as long as you keep those in what kind of relationship? Inverse relationship. So any questions about this or our intensity? We're gonna actually do some tests again this week in lab using the dosimeter again. And so we'll have our intensity will be measured. Does anybody remember what we measured? The readout, the unit that we used last week when we were using the dosimeter?
MR.
What? MR. What did you say?
Roentgen or
We can, so Roentgen is the bigger unit.
okay.
MR is just 1,000th of that, which is generally what, yeah. So, so MR, milli-Roentgen is what we use. So that's generally what we're going to be talking about, intensity in those kind of units. So, I hope this page number is right. In your Faber book, there was an example of how to solve a inverse square law problem. And so you just plug in what you know. As long as you know 3 out of the 4, you can figure out the 4th, okay, variable. So in the example on page 149, 400, and I should have put the units, MR, so 400 MR over the new, okay, so what would be the new intensity if the old intensity was 40 and the new distance is 72. So that's what it's asking. It's saying, okay, if your MR readout at 40 inches was 400, then what is it going to be if you increase your distance to 72? So the first thing you should always ask yourself when you are calculating these problems or solving these problems is, would it be more or less? So just get a general idea of what your answer should be. Okay, should my answer be more than 400 or should my answer be less than 400? And that's a one easy little way you can check, because if your answer comes up opposite of that, you know you've got something set up wrong or you punched something in the calculator wrong, something. Does that make sense? So if we're saying, okay, at 40 inches, our MR readout was 400. And now, so we're going from, we'll say this is the table. Okay, let's say we have 40 inches. Our next image we're going to do, we're going to get 72 inches. We're going to stretch, which we can't over the table, but let's just say we could. We'll stretch that tube up as far as it'll go. We'll lower that table down as far as it'll go. Would our intensity be more than 400 or less? Less. Okay, so we know that if our answer comes up and it's more than 400, we got something set up wrong. Does that make sense? So you're going to ask yourself that question on every formula that we use from here on out. Okay, should my answer be more or less? And that's just a good little check for you. So let's put in our numbers and cross multiply, as somebody said earlier. You can solve this a number of ways, okay? As long as you show your work, it doesn't matter to me how you solve it. In other words, if you don't mind working with these gigantic numbers, if that's the way you want to do it, then that's fine. We're all going to get the same answer. What I generally tend to do is reduce fractions. So I'll reduce this and then square it. Okay, it just means you're going to work with much smaller numbers. But again, it doesn't matter. You could reduce that fraction and then square each of those numbers and then do your cross multiplying. You could divide 72 by 40, get that, square that, then finish solving it doesn't matter. As long as you have your numbers in the right place, you should get the same answer. Does that make sense? You just think back to Math 109. So in this case, the new MR readout at 72 inches would be around 123.5. And that makes sense, right? Because that is less than 400. Is everybody following? You're going to get a lot of practice with these problems. We're going to do them in lab. We're going to actually make exposures and get the readouts and see if what we're telling you is really true, what really happens. So we're gonna move on because we are gonna get a lot more practice with this. So inverse square law affects receptor exposure. Because SID affects the intensity of the beam, it's going to affect receptor exposure. And so what I wanted to go back to is the picture that was in Blackboard, like main content folder for last week of the marshmallows, the s'mores. Do y'all remember seeing that? That to me is a beautiful example showing receptor exposure. Okay, so in the first, do y'all need me to pull it up? Would that be helpful? Okay. All right. Okay, so this picture here, right? If you think about receptor exposure as being how much exposure the marshmallow had to the fire, okay? Think of it in those terms. So, and relate that to the brightness on the image. So this little picture here is what I'm talking about. So based on what I just said, does this represent a lot of receptor exposure or very little? The very white marshmallow. Very little. Very little. So very little exposure. This would represent very little receptor exposure. And because it is white or bright, that's the way it's going to look on your digital image. Areas that received very little to no receptor exposure are going to be very bright. Everybody follow that? Think about your bones. They show up brighter as you've seen, as you've been doing images in the lab. Think about your markers. How do they show up? Very bright. Very bright, right? They're lead. So radiation is not getting through those. So those areas that lie right underneath your marker are not receiving receptor exposure. Is everybody following? So this marshmallow right here that's black, did it have a lot of receptor exposure or not much? It had a lot, right? Those very dark areas of your digital image, those are areas that received a lot of receptor exposure. So think about it in terms of the marshmallow has to stay in the fire longer, right, to get that dark. So that area has to receive more radiation to get that dark on a digital image. Does that make sense? Okay. Let's go back to... Sorry, hit the wrong thing. Okay. So because SID affects the intensity of the beam, it affects receptor exposure. So we said intensity is related to what? What did I have in parentheses when we talked about intensity? Quantity, right? So SID affects the intensity or the quantity of the beam, and therefore that is why it affects receptor exposure. So as SID increases, So SID is getting longer, the source to image distance is increasing, then receptor exposure is going to go down by the square of the distance change. Okay, so because of that, we have to make some adjustments if we want our image quality to stay the same. Then we have to make an adjustment to the technical factors because of that. So that's why, like in Yolanda's lab, some people were accidentally setting up using 72 inches on their upright abdomens. Okay, is that wrong to do that? Well, that's not what the book teaches, but you'll see a lot of techs actually do their upright abdomens at 72 inches because that is what we're going to learn towards the end of the semester. That actually does reduce magnification. So in other words, it makes it easier to fit the patient on there when you have a greater distance. The difference is if you are using the technique for 40 inches at 72 inches, is it going to work? No, it's not going to be enough because of what we just talked about, inverse square law. So direct square law, also known as exposure maintenance formula. So look at those words and break them down. Exposure maintenance formula. Are we maintaining exposure? That's what we're trying to do when we make changes to the SID. So in other words, think of it this way. If you make it, and we're going to actually do this more than you want to in the rest of the semester. So if we have a baseline radiograph that we do at 40 inches, let's say a foot, we have a KVP, we have a mass value that works for that particular foot thickness at 40 inches, and it's a good exposure. It gives us a quality image at an appropriate patient dose. It's a good exposure. If we want to change the distance, then we want to maintain the exposure that we got at 40 inches. We want to maintain that, right? So that we get a quality image at whatever distance we're changing to. Is everybody following? So in order to do that, then we have to make an adjustment to mass. Mass is what we're going to be changing. Because in the next couple of weeks, we'll talk about KVP more, but remember that I said last week that mass was the controlling factor for receptor exposure. We like to use mass because it doesn't affect anything else. It doesn't affect contrast. It doesn't affect the penetrating ability of the beam. It doesn't affect spatial resolution or distortion. It only affects receptor exposure. So we're going to see that we're going to make a change to mass to maintain our exposure when we make changes to our SID. So again, this is called two different things that you can call it: direct square law or exposure maintenance formula. I tend to go with exposure maintenance formula, but it can go by either name. So it comes from the concept of the inverse square law. It's used to calculate the new exposure factors when the distance between the X-ray tube and the image receptor changes. So when we have changes in our SID, we have to know what to change to keep receptor exposure the same. It is a direct relationship. So let's think about that. If we go from 40 inches to 72 inches, we already said that what happens to our intensity? If we go from this distance to this distance, say
Decrease.
it decreases, right? Decreases. So in order to, take care of that or make receptor exposure be maintained, what would we have to do to our mass value? Increase it or decrease it? Say loud. Increase it? Yes. Here, say those answers out where I can hear them. So what we're saying is, if you increase distance, then you have to increase mass to compensate for that. Doesn't that make sense? We said that mass is used to control receptor exposure. We said that if you increase distance, your intensity goes what? Down. So to compensate for that decrease in intensity, we have to do what to mass? Increase. Okay, so you can write that formula. Let's look at the one on the right first. You can write that formula as mass 1, or your old mass, or your original mass, over mass 2 equals D1 over D2 squared. So in this formula written this way, mass and distance have what kind of relationship?
Proportional, direct.
Direct. That's correct. So again, it wouldn't matter if we took that and went like this and flipped it and had mass 2 over mass 1. We would just have to make sure that we had D2 over D1 squared. It doesn't matter. You're going to get the same answers. I personally like to write it like you see on the left, where I'm just already solving for the new mass. So let me see. We got a marker over here that will write. So I tend to write, sorry, wind us off. I tend to write new over old. Okay, so that would be new mass over old mass equals what, if we're using exposure maintenance, what goes on top? Which distance? The new distance. So distance new over distance old, I just wrote that backwards, squared. Okay, so if you look at the formula on the left, what am I doing to both sides to get rid of the old mass over here? What did I just do? I'm multiplying both sides times the old mass, right? Is that not how that is written? Because now we can scratch this out and it leaves new mass equals old mass times the new distance over the old distance squared. So all I did there was just solved for the new mass. You don't have to do it that way. Again, whatever makes it easier for you to keep straight in your head, we're all going to get the same answer if we have our relationship set up correctly. And you don't forget to do what to the distance? Square it. If you don't square the distance, your answer will not be correct. It's to the distance squared. Before we go on to the next slide, I also have one more example of how you can think about this and hopefully get that concept cemented in your mind, because this is one of the basics that we're going to use from here on out in the rest of this class and next semester. We continue right on with it. So think about it this way. Think about you have a fire, okay, little campfire, okay, and you're 2 feet away from the fire. And you can feel the heat of the fire and it feels great, right? It's just right. It's not too hot. It's not, you're not still cold. It's perfect. If you move further away from the fire, what happens to the heat?
Less heat.
You feel less heat, right? You've moved further away from the source, right? So it's not as hot. It's not as warm as it was when you were 2 feet from it. So you have 2 options, right? If you want to feel that same heat, you can go back to the distance you were at originally, or what would you have to do to the fire?
Hotter.
Make it bigger, right? You'd have to make a bigger fire to feel the same heat at a greater distance. So it's the same concept with SID and mass and intensity. The further the source is away from the IR, the less intense it's going to be, the less intensity there's going to be. So the more mass you have to use to compensate for that. Everybody follow that? Okay. So if you get confused about what happens to intensity with increases in distance, think about the fire. Think about the flashlight, holding a flashlight really close to the wall and backing that flashlight up, and what happens to the brightness of the light on the wall. Think about all those examples that I've given you, and hopefully that'll help you keep this concept straight. Okay, moving on to this next slide. This is not something you have to memorize. The only one that I really want you to highlight is the 40 and 72. God bless you. So when you think about it, when you're in clinic, and let's say, for example, you go to do a patient and you get there and they're in a traction bed. So they have a femur fracture or something, and they are connected to traction, and they have a bar that goes across their bed, and you can only get, this much distance between the tube and the IR because of the limitations of the bed. Are you going to whip out your calculator and paper and pencil and plug in all these formulas and try to figure out your mass when you got 10 portables waiting to be done? Are you going to do that? Probably not. Are you ever going to see a tech do that? Absolutely not. But this is just a quick guide that you can remember when you're going back. Okay, so 40 and 72 we have said are our primary distances that we learn. That's what the book teaches. That's what we're learning, even though we're using a little bit different stuff in lab. 40 and 72 are what the standard distances are in our radiology world. So if you're going between like 40 and 72 inches, then you can say, okay, if I know what I'm going to use if I know what I would use at 40 inches, and so my example is not great. Let's use another example. Let's say you go and you've been doing a patient flat at 40 inches because they've been so ill. And now you go the next day and they're better and they're sitting up in the bed, and you can do it at 72 inches now. But the technique you've been using was for 40. Then what can you do to that technique based upon what you see on this chart? If I've been using 40 inches and now I get to use 72 inches, what would I do to my mass value that I've been using?
Multiply by 3.
Yes, multiply it by 3. Because do I need more or less mass when I go from 40 inches to 72 inches? I need more. How much more? In this case, about 3 times more. That's just a quick. So don't memorize. You don't have to memorize the whole thing, but I would say circle that one and just know that when I'm going between 40 and 6. So let's say this. Let's say I've been doing this guy at 72 inches. He's been sitting up. He gets an order late in the afternoon. I go to do him. He's flat. He's intubated, right? He's gone downhill. What would I do to the technique that I was using at 72 inches? Now what am I going to do to it if I'm using 40? Divide it by 3. Do y'all see what I'm saying there? The other easy math that you can do based upon the inverse square law is the 40. Anytime you're doubling or halving a distance. Let's talk about that in summary so you can see it. You're going to be changing, if you're doubling or halving the distance, you're going to be changing the intensity by a factor of what? Read it. 4, right? Why is it by a factor? So if I double, let's see if I'm asking right. If the SID is double, okay, so let's say we go from 40 to 80. Then the radiation intensity at the IR decreases by a factor of 4. Why is it a factor of 4?
Square.
That's right, because the distance is squared, right? So 2 squared is 4. All right, so it says if the SID is cut in half, then the radiation intensity becomes 4 times greater. So anytime you're doubling or halving distance, you're changing your intensity by a factor of 4. So that's easy math. You can do that math in your head, right? Even though you don't like to, you can, okay? So that first statement is talking about intensity. So let's look at the second statement. This is the statement. So the first statement is related to inverse square law. So anytime the question is talking about intensity, you're going to be using inverse square law, right? Inverse intensity. That's how you can remember that. If the question is asking about mass, then which formula are you going to use, or which thought are you going to think about? The direct or exposure maintenance formula. Okay, so remember that MA in maintenance and mass, just a good way to remember it. So if the question's asking about intensity, you're going to use inverse square law. If the question is asking you about what new mass are you going to use, you're going to use direct square or exposure maintenance formula. Okay, so in the second statement, it says if the SID is doubled, so now we've gone from 40 inches to 80, so 40 to 80, the mass needs to be increased by 4 times. Again, it's a factor of 4 if you're talking about an exact doubling or halving of distance. Because 2 squared is 4. If the SID is cut in half, so we go from using this long SID and we cut it in half, then the mass needs to be decreased by 4, or take 1/4 of what we originally used as our mass value. If we don't, then receptor exposure is not going to be maintained. So if you use the mass for a 40-inch SID that you should have used on an 80-inch, it's going to be 4 times too much. It's another way to think about it. Okay? Or the opposite. If you use the mass for 40 inches on something you do at 80 inches, it's only going to be 1/4 of what you needed because of the change in intensity. It all goes back to the change in intensity when we change the distance. Make sense? Okay. So we're not going to take the time right now to do this unless we get done going over the test. And then what you guys can do is begin to work on your problems. If you have your lab manual, hopefully you have access to your lab manual. That will just give us a little bit of a jump start. There's practice problems in there. The key to those problems, I would say, is until you get really comfortable with them, you know, write out what it is that you're looking for, right? Okay, old intensity, new, old distance, new distance, and actually fill in the numbers for each of those before you try to put it into your formula. If you struggle a little bit with math and word problems, you know, are not your thing, then this is what I would say do. Write out all the parts of the formula so we can talk about intensity. So again, we said if we're talking about intensity, what formula are we using? Inverse square law. You'll see it's abbreviated that way. So if the question is asking about intensity, inverse square law. If the question is asking about a new mass related to changes in distance, which formula are we going to use? Yeah, direct or exposure maintenance. All right, so that would be where you're looking for, you have old mass, you're looking for a new mass, you have an old distance, new distance. And again, you're going to do what to these distances? Square them. Make sense? Okay, so let's look at test one real quick. I do ask that you do not take any pictures. Do not have your phones out. Don't copy anything down. If I find out that's happening, this will stop. You will not see the test again. Okay, so let's. And I'm gonna go ahead and